Hello, friends. Welcome to the third online lecture of our differential geometry class. Last time I have given one example, some surface patch computations, and said I'll do one more example next time. So let me do it. So this is actually partially done last time. So I've just repeated revolution, surface of revolution. Uh, so let uh, alpha u be a curve in the xy plane. Okay, so alpha is a uh, curve in the xy plane lying in the tree space. Okay, so a curve in the xy plane. Then the surface obtained by revolving alpha about the x-axis has uh, a parameterization, a surface patch given by, remember, it was like this: uv x uv is equal to gu, and then the yz coordinates are rotated, so hu times cosine mu and hu times sine nu. Okay, here nu is an angle between 0 and 2 pi, and u is in the interval I. Okay, well, let's compute the partial derivatives then. So what are the tangent vectors along the u and x direction? So they are just so derivative with respect to u. I'll just take derivative of each coordinate with respect to u. So this is g prime and then h prime u cosine nu and h prime u sine nu. And what about the uh, new derivative? This is just 0 and then minus hu sine nu and hu cosine nu. All right. Uh, for example, if we take this curve to be alpha to be a circle as follows, uh, as an concrete example, take alpha u to be the circle uh, given by 3 plus cosine u and then sine u and then 0. So this is the circle in the xy plane. Uh, okay, at center at 3 and radius 1. So this is the curve alpha. Okay, and we rotate this about the x-axis in the xy z3 space. Okay, so you will get, if I rotate this uh, about the Okay, XYZ. So I'll get this. Okay. So when you rotate this about the not X, I mean the Z axis. Hmm, no. Okay, okay. So this is the x-axis, this is the y-axis, and this is the z-axis, and I rotate it about the x-axis, and what we get is a torus like this. Okay. All right. Now let's see why this is a why this is a surface patch here. Of course, GU is just 3 plus cosine nu. No, 3 plus cosine u, and HU is sine u. So X sub u cross X sub v, the cross product becomes the following. Here I have the ijk, u1, u2, u3, and then here I have g prime, h prime cosine nu, h prime sine nu, and then 0 minus h sine nu, and then h cosine nu. Okay, and if you compute this determinant, the I coordinate is this, and then minus g prime h cosine nu, and then minus g prime h sine nu. Okay, and then the length of this vector is the following. If you compute it, so I just square all the entries and then add them up. So you will get h squared h prime squared plus g prime squared h squared, and then I have cosine squared nu plus sine squared nu. So this is just in h squared parentheses h prime squared plus g prime squared, but this is just h squared times norm of alpha prime u squared. So this is never zero. This is never zero. This is never zero, provided that alpha is a regular curve. Regular means derivative is never zero, and alpha never uh, touches the y-axis. So here, wait a minute. H is h is 0 means it's on the x-axis, so I should say x-axis, not y but x-axis. All right. So like this one here, this is the curve alpha, and it doesn't touch the x-axis. All right. Okay. Uh, the By the way, let me tell you what is the okay. So here, yeah, let me finish what I was saying here. This is never zero, hence x is a surface patch. Okay. Let me tell you also the general case. By the way, the uh, general torus uh, has parameterization given by xuv, which is just uh, given by alpha u is this, but first of all, r plus cosine uh, u. Okay, so little r cosine u, r times sine u, 0, and this is just uh, r plus little r cosine u. Uh, okay. R times cosine u, and then r times sine u cosine u, and r times sine u sine. Right. So here gu is r times r plus little r cosine u, and hu is just r times sine u. Okay, and this is g, and then h times cosine, so it is this one. Yes, g, and then h times cosine u and h times sine u. So here this torus is the torus obtained by rotating this circle. So this is the x, and then y, and then the z direction. Okay, yeah. So this is alpha u, which is just uh, gu hu. All right. Okay. One more definition. Uh, Definition of a new class of surfaces. A ruled surface, a ruled, sorry, surface is a surface swept by, swept out by a straight line L along a curve beta. The various positions of lines generating the surface are called rulings, the rulings of the surface. Let me explain what I mean here. So here parameterization will be given like this. Such a surface has parameterization uh, given by xuv. Let's say it will be something like this: beta u plus nu times gamma u. Here beta u is called the base curve, the base curve. Uh, and this is the director. So here what we mean is this. I have this beta curve, okay, some curve beta, and then let's say this point is beta u. At this point, I have a vector, the director vector. Sorry, the director vector. Let's say this is gamma u. So beta plus gamma u is this point, but I have also this constant mu. So this is, for example, mu times delta u. So at each point, as you change nu, you just move on this line. That's why this is called the director curve, and this is the base curve. So this way, uh, of course, here you may have another director curve, and you have another line. So you have just a set of lines moving on this curve. Okay. So this is called a ruled surface, and there might be uh, several rulings on a curve, on a surface. Let me explain this on an example. Some of the classical surfaces are ruled surface. For example, consider the cone uh, given by z square equals x square plus y square, uh, which is a ruled surface. This is a ruled surface. Why is that? Let's see. Okay. Right. This is a ruled surface. Uh, this is a cone like this, x, y, and z direction. Uh, how can you see this? Why this is a ruled surface? You see, for example, consider a line like this. Okay, and then this surface is obtained by rotating this red line, you know, uh, on the surface. You may, for example, consider this curve as your beta base curve, and then this is the direction vector gamma u, beta u, and then you just move on this line and it will generate the surface. What are different rulings on this cone, for example? For example, let uh, z equals, sorry, no, y equals 0, then we get what? We get z square is equal to x square, and this can be written like this: z minus x plus z plus x. So this means this surface, the surface contains the lines z equals plus minus x, and actually they are just these lines, okay? And uh, your surface is obtained by just taking one of these lines and just rotating about the surface. Okay. Similar computation can be done also for this surface. This one is not a regular surface because, at this point the surface is not so uh, uh, is not regular, right? There is no smooth parameterization at this point, so this is not a surface. Another example, which is a surface this time, z equals z square equals uh, x square plus y square minus 1. So this is a surface like this. Here, if you let, for example, uh, y equals 0, if y equals 0, then we get this. So z square can be written like this, and hence the surface contains the lines, for example, z equals x minus 1 and z equals uh, x plus 1. Okay. I should write these are the lines. Yes, so these are the lines in tree space. All right. Okay. Now we will pass to the next uh, section. So section 4.3, differentiable functions. and tangent so let's see. I'll start with the lemma. Let alpha be a differentiable. So differentiable curve uh, on a surface sorry surface M so that the image of this curve lies inside the image xd of a surface patch x defined on a region D uh, with values on the surface M. Then there exist unique functions, differentiable functions a1 and a2 on I so that our curve on the surface is given like this in the parameterization or surface patch x for all t in I. So let me explain what's going on in the proof. So this is what's happening. I have a surface patch defined on some region D in the UV plane, and this is my surface patch. Okay, and suppose the image is this, okay, x of d, and here I have some interval I and a curve alpha here. Let's say this curve alpha is this, okay, its image lies here. Then the lemma tells us the following. Actually, there's a curve in D because we know that X is a homeomorphism, so there is this inverse image of this curve if you go by X inverse, so we get some curve here. Okay, and let's say this point is T, and then here I have uh, alpha T, and here I have uh, A1T, A2T, the U and V coordinates. How can we see this? Why this is the case? Well, it's very simple. Just consider the following composition. X is a homeomorphism, so it has an inverse. Consider the composition. First, I go with alpha and then by x inverse. So x inverse goes in this direction. So x inverse composition alpha. So this goes from interval I into where? Into the uh, you know, R2, which is the UV plane. Uh, Actually, the image is contained in D. Alpha and X are differentiable since uh, alpha and X are uh, differentiable. Actually, X is a regular uh, function, so both X and its inverse are differentiable. uh, we see that this composition has two coordinates. So when for each t, this has two coordinates, u coordinate and v coordinate. So coordinate functions are given like this for some differentiable ai. Okay, but this equation already tells us that, hence if I just compose this by x, so we get alpha t, which is x of x inverse composition alpha t. Okay, so this is just x of a1t a2t, right? Here x and x inverse cancels each other, therefore this is equal to alpha t. But on the other hand, this is just equal to a1t a2t, so this is just x of a1t a2t. So this finishes the proof. Okay. Uh, the same ideas actually gives us the following theorem. If x and y are overlapping overlapping uh, surface patches in M, then there exist unique differentiable functions u bar and v bar such that we have this y of uv is equal to x of u bar of uv and v bar of uv uh, for all uv, sorry, uv in the domain of the composition x inverse y. Let's explain this. So this time I have the following. This is my, let's say, surface. Okay, let me put it here. I have two surface patches, U, V. Here, this is the UV plane, and this is my surface patch X, and this is the U bar, V bar plane, and this is the surface patch Y. And I consider the composition. Okay, so here let me Okay, draw the intersection, paint the intersection in red. So this composition uh, y x inverse y, I go first by, sorry, y and then x inverse. So this is defined on this shaded region, and it takes values here. So, well, this composition is defined on a surface, actually in an open set in the u bar v bar plane, and it takes values in the plane, in the uv plane, uh, and its inverse y composition x inverse is given in the other direction. So this is defined in the uv plane and takes values in the u bar vy plane. So we get this. This composition at a point uv is what? So at a point like this, first I go by sorry, this is not correct. I go first by x, sorry, let me correct this. First by x and then y inverse. X takes this point here and y inverse take it here. So I go from the uv plane to the u bar v bar plane. The coordinates of this function, let's say, are given by like this: u bar of uv and v bar of uv. Okay, the coordinates of this composition. Okay, but this means what? Uh, so if I just apply y to both sides, y of this is what? X of uv. So it is just y of u bar uv v bar uv, and this is what is claimed in the theorem. What about the uniqueness of u bar and v bar? Well, these are all homeomorphisms, actual diffeomorphisms. Therefore, uniqueness just follows from you know the fact that both x and y are invertible functions. Okay, so uniqueness follows from uh, the fact that x and y are homeomorphisms. Okay, this finishes the proof. Now let me define what's a tangent vector to a surface. This will be next topic. We have seen tangent vector in R3, in R2, tangent vector to a curve, and so on, but we haven't seen what is a tangent vector to a surface. So that's what we are going to define now. a tangent vector to a surface M at a point P of M is nothing but the following: is the velocity vector, as usual, velocity vector alpha prime t0 of a curve alpha defined on an interval with image on M, where P is the image of t0 under alpha. The set of all tangent vectors to M at the point P is called the tangent space to M at P, and denoted as TPM as usual. So here is picturally what's going on. Suppose this is the tangent space. This is our surface, and okay, let me use a different color. Suppose this is our curve on the surface, and this is the point P, and our tangent, so this is alpha, sorry, this is alpha t, uh, and our tangent vector is this alpha prime t0, okay, at the point P. So this is TPM. Okay. All right, so here is the first observation. Any tangent vector in the tangent space TPM can be written as a linear combination of uh, x sub u u0 v0 and x sub v u0 v0, where uh, x is a surface patch and uh, x of u0 v0 is the point P. All right. So this is what we claim. Suppose this is the tangent space, and this is our tangent vector, let's say, at the point P. I have the following vectors: x sub u and let's say x sub v, and this vector uh, is a combination of these two vectors. Let's see the proof. So uh, let uh, uh, let's take a tangent vector. Let's take a tangent vector alpha t0 in TPM. Okay, here alpha is a differentiable curve, and uh, at t0 it takes the value t, and its velocity vector is our tangent vector. Okay, this is all right. Yes, so then consider the following. Then we know that alpha t can be written x of a1t, a2t for some differentiable functions a1 uh, and a2. Right, this is the result we proved a while ago. So this is this lemma. Yeah, exactly this lemma. So this is by a previous lemma, and then we just uh, take the derivative of this expression with respect to t. So taking d dt of both sides at t0, we get what? Alpha prime t0, so our tangent vector is equal to what? I am taking t derivative of this, so I'll apply chain rule. I'll just take first derivative of x with respect to the first coordinate, which is u, and then take the derivative of x with respect to the second coordinate, which is v, and multiply them by the derivatives of a1 prime and a2 prime respectively. So we get this x sub u uh, u0 v0, and then a1 prime t0 plus x sub v u0 v0 a2 prime t0. Here, of course, u0 v0 is just is just uh, x of this is just p, okay, which is uh, alpha t0. Okay, well, hence alpha prime t0 is just c1 times x sub u u0 v0, and c2 times x sub v u0 v0, where Ci is just AI prime T0. Okay, C1 is this. So this is C1. These are just some real numbers, C1 and C2. So I obtained this uh, expression. In particular, this tangent vector is a combination of linear combination of these two vectors. We also see that, of course, these are x sub u and x sub v evaluated at u0, v0 are also tangent vectors. Okay, so this finishes the proof. Okay, here is another definition which we will need a lot later. A Euclidean vector field. So a vector field in R3, we have seen vector fields in R3, Z on a surface M in R3 is a function. So what's a vector field? It assigns a vector to each point that assigns to each point uh, P of M a tangent vector ZP uh, to at P. Okay. So here, sorry, this is, I guess, R3. This is the Euclidean vector field. If ZP belongs to the tangent space for all P in M, then we say that Z is a tangent vector field to M. If ZP is normal to this plane for all P in M, then we say that Z is a normal field, normal vector field on M. So suppose this is our surface. Uh, so a tangent vector field is something like this. We have, say, some curves on our surface, and the velocity vectors of these curves are tangent vector fields on the surface. What's a normal field? Normal field is something like this. So at each point, we pick a vector which is normal to the surface, okay? So something like this. So this is a normal field, okay? Normal field. And this is a tangent field. Okay. Uh, Let me give a lemma about this vector fields. If our surface is a level surface, let's say given like this, a level surface of a function is a level surface uh, in R3 for some differentiable function g from R3 into R, then the gradient vector field sorry given by this is a normal vector field on M. Okay, so suppose our surface M is a level surface of some function. So this is just G inverse of C. Okay. In other words, it consists of points. Let's say P1, P2, P3 in R3 such that G of P is equal to C. Okay. Then uh, suppose M is like this. So what we claim is this. At any point P, the gradient vector uh, is perpendicular to the surface. Okay, that's the claim. And this is easy to prove. Here, of course, G is a smooth function, differentiable function from R3 to R. Okay, so to show that this is normal to the surface, I have to prove that uh, need to prove this vector is perpendicular to all tangent vectors. For all tangent vectors alpha prime t0 tpm. Here, of course, p is just the value of this function at t0. Okay, how can we prove this? Let alpha be a smooth curve as usual, so which takes the value p at some point t0. Since alpha t is in M, we see that g of alpha t is equal to c for all t in alpha. Okay, say alpha t has coordinates alpha 1t, alpha 2t, alpha 3t. Then g of alpha 1t, alpha 2t, alpha 3t is equal to c for all t in I. Take derivative, take d dt of both sides to get, well, t derivative of this is a constant real number, so it is 0. So I just take t derivative of this. What is the t derivative of this? Well, I have to apply chain rule. First, the x derivative of g, and then the x coordinate is alpha 1, and then alpha derivative of alpha 1, let's say at t0, and then x1 derivative, and then x2 derivative alpha 2 prime t0 plus, you're right. What is this? Well, this is just the gradient vector. Of course, this is, you compute this at t0, and alpha t0 is p, and then the dot product of this with this vector alpha 1 prime t0, alpha 2 prime t0, alpha 3 prime t0. But what is this? This is just the gradient of g at the point p, dot product alpha prime t0, and this is what we wanted to show. So this means the gradient is perpendicular to this vector. Since alpha t was arbitrary, we see that the gradient at the point P is perpendicular to the tangent space. And this finishes the proof. Okay, a quick example. Let g be this function from R3 to R given by g x1, x2, x3 is just sum of squares. Okay, and let sigma be this gadget c, where c is just some r squared. So this is the point where the sum of squares is equal to r squared. So this is a sphere. Uh, Hence, is the sphere centered at the origin with radius so what is the gradient then? Then gradient at any point is what? So I'll just take derivatives of this function with respect to x, y, z. So this is just 2 x1, 2x2, and 2x3 at the point P. So this is just 2 times P1, 2 times P2, 2 times P3. Since P is the point P1, P2, P3. Okay. So this gives us the following picture. At any point P on the surface, let's say here, gradient is just this vector and it is normal to the surface. Okay. So our tangent space is something like this. Okay, and this is normal to the tangent plane. All right. I'll finish with the final definition. Let V be a tangent vector to M at T, and let F be a differentiable function on M. The derivative, remember, vectors eats functions and gives us real values, and they are nothing but directional derivatives of these functions along the vector v at the point P of f with respect to v is the common value of this gadget. So f composition alpha t evaluated at 0 for all curves alpha with alpha 0 at P. So this tells us the following actually. If I want to take derivative of a function at this point along this vector, all I need is a curve passing through this point at a point, let's say 0, and then the derivative is nothing but, so the derivative of f at uh, this tangent vector is nothing but, you just need to take the derivative of this composition. Okay, this is a function of t, and you compute this derivative and evaluate it at t equals 0. This is the definition, okay? This is the definition. Here you should uh, uh, think about this. I said the common value. What I mean is the following. There are, of course, many other curves, not just this alpha, but many other curves. Let's say another curve like this, beta, and it it may have the same tangent vector. So alpha prime t 0 could be equal to beta prime 0, and they are both phi. And what we claim is that these two things are the same. So this can be written like this. So for all curves tangent to this vector having the same velocity vector at the point P, these derivatives are the same. Why these are the same? Well, it is because of the chain rule. If you just compute these derivatives, all you need is the derivative of alpha at the point 0, but derivative of alpha at the point 0 is the same as the derivative of beta at the point 0. Therefore, it doesn't matter which curve you pick. You may pick alpha or beta, you will end up with the same result. That's why we say here the common value. All right, so this finishes uh, section 4.3. I'll stop here, and then next time we will start chapter 5. Till then, take care. I'll see you later.